Okay, now let's talk about the second translation theorem in the same section, 4.3. So, consider the step function. So this is the same notation as in the book. 0 up to time a, and 1 after. Okay. So here's the theorem. If you have the product of a function with the other step function, well, what is that? This is it's the function times the step function. So it restricts it to a to infinity. Because it's 0 from 0 to a. Okay, then you shift it back to 0. So t tilde is equal to t minus a. But of course, the variable is a dummy variable. So you get e to the minus sa times the Laplace transform of f of t plus a s. Okay, so that's the identity. Okay. A variation of this is if you let gt to equal ft minus a, you get the following, right? You get t minus a. I might as well actually call it this. No, let me follow the notation. So ft minus a, ut minus a, s, and then sa, but you just get f of t on the right. Right, so here you have t plus a, here you have t. You have t, you have t minus. So if you apply star to gt, you get this. Okay, so now let's apply these two identities. I'll call this a double star. It's the second version of the second translation theorem. Solve the IVP. Y double prime, 2y prime, y equal to t, ut minus 1, with y 0, 0, and y prime 0. If you like a circuit analogy, so for circuit, it says that your voltage pops up at time 1. So up to time 1, you're 0 voltage. This is the voltage. And then after time 1, it increases. All right. So as usual, we have the formula yt equal to Laplace inverse the homogeneous part, so s squared plus 2s plus 1. The left hand side, right hand side, t ut minus 1. And then the two initial data are both 0. Okay. So first we have to find this Laplace transform. So we use the translation theorem, right? So for f of t equal to t, we get e to the minus s, and then Laplace transform of t plus 1. So let me call it plus 1. Okay. So e to the minus s. Then we use linearity, and lt to the n is n factorial over Sn plus 1. So this is 1 over s squared, and this is 1 over s. Okay, good. Now we can return to our inverse. So y of t is equal to the plus inverse of s squared, s plus 1. So I factored the denominator. Okay, so now we have to find the Laplace inverse of these two guys. By partial fractions, s squared, s plus 1 squared needs to equal a over s, b s squared, or else c s plus 1 and d s plus 1 squared. Okay, so yeah, if you do the computations, you get 1 over s, minus 2 over s, 1 over s squared, 2 over s plus 1, and 1 over s plus 1 squared. Okay, and then the other guy, you get 1 over s minus 1 s plus 1, and minus 1 s plus 1 squared. So these are the two, and let's return. So e to the minus s times what? So in fact, I can group things together. Let me do it. So 1s 2s plus 1. So this is the first factor. That was the first guy. This is the second term. Minus 1s plus 1. Minus 1s plus 1 squared. But yeah, you can, you can group things together. This with this, and this with this. So you have cancellations, and you're left with the following. Square term, and then one more Laplace inverse. So here I use the linearity of the inverse. Okay, good. Okay, almost there. Let's see. Yeah, almost there. So now we can use the translation theorem. So this is e to the minus s. Let me put the minus inside. Laplace transform of 1. Okay, minus s. Laplace transform of t, right? And then Laplace transform of exponential. Okay, so minus t. All right. So here we will use that the Laplace transform e minus sa f of t. So if you take inverse of this, you get f of t minus a times the step function. Okay. Here we're using the second version. This is the second version of the translation. Okay, so right. So let's see. Let me do one, and I'll just write the rest. So Laplace inverse of e minus s. Here f of t is 1. So it's just 1, right? This doesn't change. It's a constant function. And then times ut minus 1. Actually, let me do a polynomial one too. So e minus s, Laplace transform of t. Here f of t is t. So you get t minus 1 times ut minus 1. Okay? All right. So the solution will be as follows. Let me write it. Minus step function times 1. Step function times t minus 1, right, up here. And then ut minus 1 times e to the minus t minus 1. And that's the solution. But I have a clean form. So this guy is 0 for t to 1. And it's the following guy plus t minus 2 when t is bigger than 1. Yeah, I can draw it. So the solution is as follows. Your 0 up to time 1. And then at time 1, this guy is 1. And this guy is also 1, so 2. And what happens is you grow linearly. You're a bit faster. Right, like this. This is a transient term. All right, good. So that's the solution for the charge, if you like. Where the voltage is of the form T ut minus 1. Okay. We have time for one more. Yeah, let's do it a little bit quicker. I'll just give you some of the main ideas, so at least you have another example. Solve the IVP. I will say what f is. Y prime of 0 is 1. So I wanted to do an f you haven't seen before. So I took it to be 0 from t to pi, 1 between pi and 2 pi, and then 0 again. So this is the step function, like this. 0, 0, 1. Okay. So let me write a little bit. So as before, we want yt. So we have, oh yeah, and also make the comment that f is the difference of ut minus pi and ut minus 2 pi. Okay, so this is from the formula that you can always just use, just plug in the numbers. Here we have plus 1 because the initial data is 1. Okay. So, right. So I'll just talk about a little bit about f, and I'll just write you the final answer. So, right. So L of f is as follows. So here again, I use translation theorem, but for the constant function. So for, times 1. So the first guy gives you e to the minus pi s, right? So a is pi here, and then a minus 2 pi s. Okay. All right. So finally, we have yt will be the Laplace inverse of the following: e minus pi s, s squared plus 1, e minus 2 pi s, s squared plus 1. So I leave it to you. This is again a partial fraction. So let me just write you the final answer after you do partial fractions. So we have ut minus pi ut minus 2 pi and plus sine t. Okay, so that would be the final answer. Okay, thank you.